Welcome to the Deep Dive. We're here to cut through the noise and get straight to the insights you need.
That's the plan.
Today, we're plunging into network meta-analysis, or NMA. It sounds a bit technical, maybe?
It can be, but the idea is actually pretty exciting. It's not just comparing, say, treatment A against treatment B.
Right. NMA lets you compare lots of treatments all at once. It synthesizes all the evidence to see how they stack up benefits, harms, the whole picture.
Exactly. It's kind of the next level for evidence synthesis, especially when you've got complex health decisions, maybe dozens of options to consider.
And people are noticing these, right? I mean, you see NMA studies popping up way more often now.
Oh, definitely. There's been almost exponential increase in NMA publications. It shows how important it's becoming.
What makes it so powerful, fundamentally?
Well, it cleverly combines both direct evidence, like from head-to-head trials, and indirect evidence. You get a much more complete picture.
Ah, okay. But that power, I imagine, comes with complexity.
For sure. And a big part of that complexity, and honestly a major debate for a long time, has been about the statistics behind it. Specifically, the choice between two main approaches, Bayesian and Frequentist.
Right. That's the core of what we want to unpack today. We want to sort of demystify these big statistical ideas.
Yeah, give you the crucial insights without, drowning you in jargon.
Exactly. So you can walk away knowing what's what with NMA,
Yeah.
maybe with some surprising facts, and really understanding what makes for reliable results.
Sounds good.
Okay, so let's dig in. Bayesian versus Frequentist. What's the core philosophical difference between them when we're talking NMA?
Okay, think of it maybe like this. Frequentist statistics looks mostly at the data you have right now. It asks, okay, if we assume X is true, how likely is it we'd see this data?
Right.
It thinks of the true underlying effect, like how well a drug really works, as some fixed but unknown number out there. And you're trying to estimate that number based on how likely your observed data is.
So it's about hypothesis testing. And you end up with things like a p-value or maybe a point estimate with a 95% confidence interval, a CI.
Precisely. That CI is about, if you did the experiment loads of times, 95% of those calculated intervals would contain the true value. It's about long-run frequency.
Okay, got it. And Bayesian, how does that differ?
Bayesian takes a different angle. It's maybe more like a detective building a case.
Yeah.
It uses probability differently. It focuses on the probability distribution of the parameter itself, given the data you've seen.
The probability of the parameter.
Okay.
But crucially, it also formally incorporates what are called prior beliefs, basically any external information or existing knowledge you have before you even look at the new study data.
So like an initial hunch, or maybe results from previous similar studies.
Exactly. You start with some initial belief, maybe vague, maybe quite specific, and then you use the new data to update that belief.
That sounds, pretty intuitive, actually. How does that combination happen? The prior belief plus the new data? It happens through some pretty sophisticated computational methods, often things called Markov chain Monte Carlo simulations, MCMC for short.
MCMC.
Think of them as really fast computer simulations that explore the possibilities, combining your prior beliefs with the likelihood of the data until they converge on what's called the posterior probability. That's your updated belief.
And instead of a confidence interval,
You get a 95% credible interval, or KI.
and that KII, you interpret that differently, right? It's more like there's a 95% probability that the true value lies within this range.
That's generally how it's interpreted, yeah. It feels to many people like a more direct statement about the parameter itself.
Okay, so two different philosophies. How do these translate into actual NMA models? What do they look like in practice?
Well, both sides have developed various models. Frequentist NMA often uses approaches based on graph theory or multivariate meta-analysis. They typically work with the relative treatment effects like the odds ratio comparing drug A to drug B, usually at the study level.
And the Bayesian side.
There, you often see hierarchical models, multi-level models. The Liu and AIDS model is a very well-known example. And generally, yeah, Bayesian models are often seen as having more inherent flexibility, especially in dealing with uncertainty.
How so?
Well, in Bayesian NMA, you assign these prior distributions not just to the main treatment effects, but also to things like how much the effect varies between studies, the heterogeneity.
Right, those priors again.
Ideally, you want the data to drive the results. So researchers often try to use non-informative or minimally informative priors. The idea is to let the observed data speak as loudly as possible.
But is that always what happens? I seem to remember reading that sometimes these priors aren't very clearly explained in published studies.
That's a really important point, and yeah, it's been a criticism. Some reviews have found that quite a few Bayesian NMAs, even in top journals, don't actually specify the priors they used, especially for heterogeneity, or they don't give a clear reason for their choice.
That feels like a potential weak spot if the starting assumptions aren't clear or justified.
Exactly. How much can you trust the final output?
Right.
It's particularly tricky with that heterogeneity variance, basically. How much the true treatment effect might wiggle around between different studies.
Right.
If your prior belief about that wiggle room is, say, too vague, or if you don't have much data to pin it down, the prior itself can end up having a really big, maybe undue influence on the final result. It's like having a strong opinion that's hard to shift, even with new facts.
That's crucial. Okay, so beyond the core philosophy and the priors, another big thing in NMA is how the data gets used, right? This idea of contrast synthesis versus arm synthesis.
Yes, that's another key modeling choice. Contrast-based NMA, which is common in both frameworks, focuses on modeling the relative effects, directly the log-odds ratio, the hazard ratio, comparing treatments within a study.
Okay. And arm-based.
Arm-based models look at the absolute effects in each trial arm separately, like the probability of success in the group getting drug A and the probability in the group getting the placebo. Currently, these arm-based models are pretty much only available within the Bayesian framework.
That's interesting. Only Bayesian for arm-based right now. So why choose arm-based if it's limited like that? And I think I've heard some criticisms too.
You have. Critics sometimes worry that arm-based models might mess with the randomization principle of the trials because you're looking at arms separately, and absolute effects can just be more variable than relative ones.
But there must be advantages.
There are, and they can be quite compelling. Arm-based models let you bring in arm-level information, like average patient age in that arm, to explore effect modifiers. They can incorporate single-arm studies, which is super useful for things like cost effectiveness. And they can often handle missing data more easily. And importantly, they can allow for different amounts of heterogeneity for different comparisons, which many contrast-based models assume is the same across the whole network.
Let's talk about that heterogeneity assumption. You're saying many standard models, Frequentist or Bayesian, assume this common heterogeneity variance, that the wiggle is the same everywhere.
Yeah, it's a common simplifying assumption. It makes the models easier to fit, needs fewer parameters. But
It's not always realistic.
it might not be. And it can cause problems, especially in sparse networks, networks with few trials or certain structures, like star networks where everything is compared to one reference treatment.
What kind of problems?
You can get weird results. The heterogeneity estimate itself might not be reliable, and counterintuitively, the final confidence or credible intervals from the NMA can end up being wider than if you just looked at the direct or indirect evidence separately, which isn't what you want.
So what do you do then?
Well, interestingly, in those tricky situations, sometimes switching to a fixed effect model, which basically assumes zero heterogeneity, can actually work better and give more plausible results.
Wow, okay. So assuming no variation can sometimes be better than trying to estimate variation badly.
In specific circumstances, yes. It highlights how complex model selection is.
It really does sound complex. So many choices, so many nuances. Which brings us to the really big question here.
The million-dollar question.
Exactly. After all this theory, all these differences, what happens when you actually compare Bayesian and Frequentist NMA models head-to-head in practice? Do the studies show one is actually better, more accurate, less biased?
Right. And perhaps surprisingly, given the historical debate, there actually haven't been a huge number of studies doing direct comparisons, especially with all the latest model variations.
But there have been some.
Yes. And the evidence we do have is pretty consistent, and maybe a bit anticlimactic for the debaters.
Ooh. Tell me more.
Several studies, including a significant one that reanalyzed data from 14 published networks, and others that used simulations, especially for those tricky sparse networks. They largely came to the same conclusion.
Which was?
That there seems to be no important difference in performance, bias, or error rates between Frequentist and Bayesian NMA models, provided that an appropriate model is chosen in the first place.
Wait, really? No important difference. That's huge.
It kind of is, yeah. It suggests the big philosophical fight might be less critical for the actual results than we thought.
So it's not about Team Bayesian versus Team Frequentist.
It seems not, at least in terms of getting the right answer. It's much more about the specific features of the model you build and whether those features are appropriate for the data and the question.
Like what kind of features?
Like, did you use a fixed effect or a random effects model? Was that choice justified? Is it a contrast-based or an arm-based analysis? How did you handle heterogeneity? Those kinds of decisions seem to matter more than the underlying Bayesian or frequentist engine, so to speak.
Okay, so Bayesian models might offer more flexibility for complex things, like you mentioned ARM-based models or disconnected networks,
They often do, yes. That flexibility is a real plus. But it comes with strings attached.
such as,
Well, they generally require more statistical expertise to run properly. You need to be comfortable with the software. You have to make those careful choices about prior distributions we talked about.
right, the priors.
And you need to check that the MCMC simulations have actually worked correctly, that they've converged on a stable answer. That's not always trivial.
Okay, so Bayesian, flexible, but more demanding. Yet, you mentioned earlier, or maybe the source material suggests, they are actually used more frequently.
That does seem to be the case.
Why do you think that is? If performance isn't necessarily better and they're potentially harder to use?
Well, one likely factor is the historical availability of really good free software packages for Bayesian NMA, things like WinBudGS, OpenBudGS, JADGS, Stan. They made it more accessible.
Practicality. Software matters.
It often does, and maybe some earlier frequentist methods had their own complications or limitations that steered people towards Bayesian options, but the core message from the comparisons holds.
Choose the right model, regardless of the framework.
Precisely. Focus on the appropriateness of the model for your specific situation.
Okay, this is genuinely the key insight, isn't it? It shifts the focus. It's not about this big theoretical battle, but about the nitty-gritty of good modeling practice.
Exactly. When you're looking at an NMA, the latest thinking suggests you shouldn't get too hung up on whether it says Bayesian or frequentist on the tin. What you should focus on
Is whether they used a model that makes sense for the data. Does it account for important factors? Are the assumptions reasonable? That's where the critical evaluation should be.
Let's recap that for everyone. The bottom line from the empirical studies is no major difference in performance, bias, or errors between the two frameworks if the model itself is appropriate.
Right, focus on model features, applications, assumptions, not just the statistical school of thought.
And just to remind ourselves of those core differences one last time, frequentist sees parameters as fixed, unknown, uses likelihood, gives confidence intervals based on long-run frequency.
While Bayesian treats parameters as having probability distributions, incorporates prior beliefs, uses MCMC, gives credible intervals representing degree of belief.
And we've seen that choices like fixed versus random effects or contrast versus arm synthesis often swamp the impact of that fundamental framework difference.
Definitely. And while Bayesian offers that neat flexibility for ARM-based stuff, disconnected networks, maybe more complex heterogeneity structures, it comes with the need for more stats expertise, careful prior selection, checking convergence, which are real hurdles.
They are, and yet, as you said, they are widely used, quite possibly driven by the availability of powerful free software.
So bringing this all home for you, the listener, you're increasingly likely to encounter NMAs. What does this all mean for you?
Well, it means you can perhaps worry less about the label Bayesian or frequentist.
And worry more about the how. Given that how the analysis was done seems to matter more than the underlying philosophy, maybe the question to ask is different now.
What kind of question?
Well, perhaps when you see an NMA, instead of just asking, was it Bayesian or frequentist, or you might ask, what kind of model did they actually use? Why did they choose random effects over fixed effect, or vice versa? If it was Bayesian, how did they choose their priors, especially for heterogeneity? Did they check convergence? Was an ARM-based model used, and why? Basically, probing the specific choices made in building that model to ensure the findings really are robust and relevant to what you care about.
That sounds like a much more productive line of questioning. Asking those questions gets you closer to understanding the real strength and potential weaknesses of the evidence presented.
A provocative thought to leave you with.